আমি actually yes Raukel. বললাম যে অ্যাকোমোডেশন দিয়েছে হাই-ফাই হোটেলের নাম
রাজা মহারাজারা অনেকবার
মানে আমার তো পরের দিনও হ্যাংওভার ছিল আর কি হ্যাংওভার ছিল
Okay, so welcome to the weekly colloquium of the School of Astrophysics. It's our pleasure to welcome Professor Indranil Chattopadhyay from the Aryabhatta Research Institute of Observational Sciences as our speaker today. So Indranil Da, as we call him, did his undergrad and MSc from Calcutta University, and then went to the Eisenberg Center to work on his PhD with Professor Sandip Chakraborty. After his PhD, he did postdoctoral research in South Korea and Belgium, and then he came back and became a faculty member at Aries, where he has been ever since. So Indranil, first of all, is a friend of the department. He has visited many times. Previous students have worked with him on research projects, and if you ask him nicely, one of you may do work with him in future. So Indranil's expertise is on fluid flows around compact objects, so it could be inflow or outflow. So Professor Sandip Chakraborty, his advisor, is a very famous astrophysicist who has worked on this topic, and there are more than 50 students of him who are in various positions in and outside of India, and I among many of them, I think Indranila's work has sort of gone beyond that, and he has worked on outflows and he has included things in his theoretical work that was sort of not done in his group before. So that way I find his work very more creative, and also he is interested in connecting his theories with observations, and that's where sometimes we try to collaborate. We haven't written a paper together yet, but maybe that will happen. Maybe one of you will be the lead author in that paper, like it happens. So without further, so there are many stories, but since this is recorded, I cannot tell you.
No, we can edit that part. We can actually edit that part.
Okay, so I think the one normal story that doesn't need to be edited is the first time I remember, because I never did any research in India before 2013. So, I mean, we had a research project when I was doing my master's, but there was no research done in the project. I just went to the lab and came back. Anyway, so I came back and I was in this conference and I saw that I knew that that it does work on accretion disk and fluid flow, etc. But I noticed that there was this conference on things related to compact objects, AGNs, black holes, binaries, etc. And I noticed that there's one person that is continuously asking questions, particularly related to the disk jet connection and how the outflow can form and so on.
And you were the
And
speaker, right?
I was one of the speakers, but there are many speakers, and he was asking questions to almost all of them. So that's how I noticed that, okay, someone who, his interest in jets and outflows and connection with disk, etc., that became very evident at the time. So since then, I know Indranil as he is. So that's the simple story. Okay, so without wasting more time, since we have to finish within 4:15, so that this room can be used for the class. So let's have Professor Indranil.
Just one comment. When
Yeah.
anybody who, if somebody does project with him, he or she will have an opportunity to stay in this picturesque place. Actually.
That's
So you just want to you invite us or we want to spend some time.
So our next picnic will be there.
So yesterday I was in Shaha Institute and Manosda of Shantiniketan. He was there. So the security stopped me.
Oh.
And then Manos, when I entered, Manos said, you should have said that you shouldn't stop me. I handle, leopards there. There are a lot of leopards here. Okay. So,
Yeah.
Fine. So yeah, so this is the hill which is where Aries is located, and this is the 1 meter telescope. I sit in this room. Okay. Yes, and we have another campus which is around 60 kilometers from here, where you have the country's the largest optical telescope, Devastal. Anyway, so that's me and my coordinates. All right, so. All right, so let's. I have written it story of black holes, but essentially it's not much. I mean, I'll be just pointing to a very simple thing. Just it's sort of an introduction to start my talk. I was last night. This is a new work, so I didn't have any old slides. So last night I was spending a lot of time trying to figure out how to start my talk. Because that's the most important part of a talk, how we start it. Okay, then the rest of the things follows. I mean, if you have done it. If you have not done it, that never works. Anyway, so the story goes like that there were some curious objects, after the Second World War, the observations became better. Okay, that's because people wanted to fight and they were trying to be spies, the US and the USSR. And they're looking at each other. One of the offshoot of that is that your observational capabilities in various wavelengths, electromagnetic wavelengths, increase leaps and bounds. Okay, entire radio astronomy was an offshoot of radar technology. Radars were used to figure out, enemy planes. Okay, and also, I mean, they were also using X-ray detectors to figure out which guy is blasting or testing a atomic bomb or doing something more energetic on it. So that's how all the X-ray telescopes later on came out. Okay. Yeah. So you know that story of GRB, right? The Vela satellite. So that initially US thought that USSR has blasted some very energetic bomb. Okay? Later on, they figured out it is not terrestrial. Anyway, so the point was that astronomy is pretty old, so we know what is stars. Okay, and stars are far away, so they're point-like objects. Okay, but there were few point-like objects they also found, whose if you can plot the spectrum, if the fluence is good enough, then they were not like black body spectra. Okay, stars have black body spectra. Okay? So in PhD interviews later on, if someone asks you to give you an example of a black body, you should say sun or any other star. Okay. Anyway, so they didn't have a black body like spectra. So they were pretty curious. What was it? Okay. So what Martin Schmidt did was he was looking at the spectra of this object called 3C273. And by the way, this is a Hubble image. So they saw these H alpha, H beta, H gamma, etc. lines, the hydrogen lines, but these are all shifted. Okay, and so from the shift, they could figure out what was the redshift, and the redshift gave you the distance, and it turned out to be their extragalactic. So what is the first conclusion you can get from it? If something is close by, what you are getting is an electromagnetic radiation, right? So you are counting the number of photons that are, per unit time, per unit area that's impinging on your detector, right? But if it is close by, then it's basically 4 pi r squared. So luminosity will be small. But if it is further away, the luminosity will be very high. And he estimated the luminosity to be around 10 to the power 46 arcs per second. Okay. So if that is the case, that means that the luminosity is enormous. Okay. Sun's luminosity is around 10 to the power 33 arcs per second. Okay, so you can understand not only orders of magnitude, it's really, really massive, right? So if you take an example of very luminous stars, sun is not the most luminous stars, like O-type stars, okay, which can be 1,000,000 times more brighter than a sun. But even then, you need 10 to the power 7 such stars to fire this kind of power. Okay. So it's extremely luminous. The second point, of course, is that people knew it's basically power law spectrum. Okay, you have those emission lines, but you also basically what you see is a power law, and you see the power law in every. Later on, of course, in 1964 they didn't know it, but if you look at any in any energy range, okay, there is a power law, right? So something very energetic is going on. Okay, so what they could understand, okay, this is a common story I tell. In 1963, Roy Kerr presented his Kerr solution in one of the Texas symposiums. Okay. So I asked Roy Kerr that, so you must be very famous after you presented your Kerr solution. He said, when I presented, there were 3 people there in the audience. One of them was the chairman, other one was my friend, and the third one already left before I started my talk. In between, not before. He started his talk and he left. So he somehow caught that guy later on, okay, and asked him that, I tried to, this is a black hole solution, this, that, rotating black hole solution. Nobody did it before. I did it for the first time. So, why didn't you attend? He replied, the other fellow replied that these are mathematics, okay? This is not physics, okay? I'm not interested, okay? But soon after, that is in 1964, so when they found this kind of luminosities along with power law spectra, they immediately realized that normal nucleosynthesis will not be able to generate this kind of emission and will not be seen. These are unresolved. These objects are unresolved. You cannot resolve it. You couldn't resolve it then, you cannot resolve it now. It is so small. So essentially, you have a compact object and it is emitting so much, radiation. The only way you can do it is if there is a matter accreting into a very deep potential well. The only solution can be that accretion onto a very compact object is the only viable alternative. Why do I say that? Very simple. You have a ball and it drops down. This amount of energy it will give up in order to fall down, right? As simple as that. Deeper the potential well, more energy will be released. Now comes physics, that how that energy released will be utilized to produce radiation. That is detailed physics. Okay. We at this moment will not be interested in detailed physics. So people around in astronomy understood it has to be a black hole. Otherwise, you cannot explain these kind of luminosities. Only black hole has this deep potential well. Okay. So, I mean, again, I think your PhD students have already done it, but basically the gravitational energy release, if your mass supply is around dm/dt, would be gm with r, dm/dt by r, right? You multiply c squared divided by c squared, and you can write the luminosity or the brightness in terms, not brightness, power rather, would be like eta c squared, like whatever. So this is like the rest mass energy, the rate of rest mass energy supplied, right? And eta will, you can say it's the efficiency, right? And the efficiency comes out to be the radiation, gravitational radius by the radius of the object, right? So the maximum it could be like 1. For an extremely rotating black hole, eta is 1.
R is what?
R is the radius of the
Object.
object. Okay. For sun, this is like 10 to the power minus 5. So for normal stars, accretion is not a very efficient process because the potential well is not large enough. Okay. All right. So then tons and tons of observations, and you can see the spectra of the spectral energy distribution. This is a Cygnus X1. This is not an AGN. This is again extra binary, but the first poster boy of black holes. Okay, so you know that, right? Stephen Hawking and Roger Penrose. They had a bet, right? And so that the bet was about Cygnus X1. Okay, so that's the first poster boy. So anyway, so you this is a spectral state. You can see that the power law is positive. Here the power law is negative, and so there are different spectral states. And these are, of course, I have done it in keV, the flux is keV centimeters squared per second. But if I have done it in ergs, you will see that these are like 10 to the power 38 ergs per second. Okay, so it's around 14 solar mass central object, but luminosity is way higher. Okay. All right. So, but not only matter falls in, there are also jets coming out. So this is like SS433, which is again extra binary, but this is M87, which is an AGN, right? So this is the stack like 20 years of data, and you can see that matter coming out. So not only matter falling in, there are matter coming out as well. Okay.
That was a binary. That was not a binary.
This one is a binary. So this is in radio. The secondary in SS433 you don't see much. You can see it, but it is shrouded with lots. There's a Wolf-Rayet star. So Wolf-Rayet star emits a lot of outflows. So the whole thing is sort of surrounded by the matter that has been ejected by the Wolf-Rayet, the secondary. Okay, it's very difficult to look inside. This is, of course, in radio. Okay, so ideally, a correct accretion-based model should incorporate all these features. But today, I'm not going to talk about these. These are all luminous black holes. Okay. Whether it's extra binaries or AGNs or whatever, they are very luminous. Today, what I'm going to talk about is this research has gained a lot of importance, which I'm trying to talk today, after LIGO came. So what did LIGO do? You know about LIGO, right? I did not talk about LIGO much.
We talked like 2 weeks back on.
Yeah, so I'll not spend time on it. But what LIGO did is it basically detected isolated black holes. Okay, so you have black holes which are, going around each other, merging and forming another black hole. And these are bare black holes. It's not accompanied by matter, which is accretion, whatever I talked before. Okay, it's not that. So the population of black holes in the universe or in our galaxy, these are all, how do you estimate them? These estimations are from stellar evolutions, right? But what LIGO shows us is that there are far many black holes than we actually accounted for. Okay, so the question now is how to take an estimate of these black holes. Okay, how will we see? Can we see them? If it is bare, we will not be able to see them. But those bare black holes will be moving in the interstellar or intergalactic medium, right? And so then they can attract the interstellar medium or intergalactic medium, and then they can have some kind of an accretion. And if you have some kind of an accretion, it will glow. And if it glows, then we can detect them. But can we do that? So that is what we're going to talk today. Oh, so this Nobel Prize. Okay, yeah, so that's what so the number of statistics of isolated black holes. The first work on isolated gravitational object, accretion onto an isolated gravitational object, was done long time. The first paper was in 1939 by Hoyle and Littleton. Hoyle was a student at that time. Okay, what were they interested on? Where is it?
The last I We will study whether accretion is can form in BHL process.
No, that is fine. But I was talking about yeah, maybe later. Yeah, maybe next slide. Yeah. I mean, where is it? Come on. বক্তব্যটা হচ্ছে okay, I don't know.
We theoretically allow a dispersion. That is the question.
That is fine. That is what I will try to talk about. But interesting thing about this paper 1939. Okay, I don't know where I put it. So it's written by Littleton and Hoyle. Littleton was, I think, the guide, and Hoyle was the student. So what they were interested in, I mean, when I read that paper, the title of the paper, it's astounding. The title of the paper was Effect of Climate Change. Effect of climate change by accretion onto stars. So they were worried about how ice ages form. Okay. So they were studying a sun-like star. If it moves through interstellar medium, So it will accrete matter. So that will affect or reduce the solar radiance. So that whether that can cause ice ages or not.
That cite this paper on the.
Yes, this 1939 paper. I thought I don't know what I did. It's a last night's problem, okay? When you are sleepy and you do something, you think you have done, but you have not done it. Or maybe I have done it.
There is a normal star or?
Normal star. Okay. So this problem, what they did it in particle limit. That is essentially they thought about there's a star and a lot of particles around, okay, and how they will capture the particles. Okay. I don't know, where did I put it? Anyway, fluid mechanics. Yeah, I mean, whatever I had in my mind, it's not there in the slide. Okay, so all right, I'll come to that. So what we do is essentially, I'll come back to this later on. I mean, somehow I made a mess. What we'll be studying this accretion is we'll assume that the matter is fluid. Okay. Why do we assume matter is fluid? Because gravity, especially if it's a strong gravity, it will attract and it will squeeze and stretch and squeeze matter around. So that will make it something like a fluid. It will not. I mean, the stars will also not maintain the star structure. It will get squished and it will get spread and it will sort of go like a flow. So all this accretion or jet and all this business is essentially studying fluid mechanics. All right. All right. So what are fluids? Yeah, sure.
This primordial black hole should have been evaporated by now, no?
No, depends on the mass.
It depends on the mass, but there is a limit from the 10 to the 14 kg to 10 to the 21 kg.
Right, there is
Yes.
a limit
Yes.
at the evaporation time within the age of the universe.
But there is a horizon. I mean, it went. It didn't go out of the horizon.
No.
No, it didn't. Yeah, it didn't go out of the horizon, but due to Hawking radiation.
Yeah, these are Hawking. Yeah.
We estimated that thing in our statistical mechanics.
I think 10 to the power 15 grams and above primordial black holes are supposed to survive.
Yeah, they are supposed to survive.
But then by this one, you know I mean, how they are distributed. Distribution function is not known yet.
No, it's not.
Log normal.
It's not known.
People do the screens.
I mean, until you detect something, whatever you write doesn't make sense. Okay, so what are fluids? Fluids are a collection of interacting particles. These are not long ranged. I think you guys know, but maybe for BSc students. Okay, so basically fluids are a collection of particles where the information of individual particles are lost and it is replaced by macroscopic properties like density, pressure, temperature or thermal energy and so on, right? And so pressure is like average momentum flux. These are definitions, okay? And average kinetic energy of this random motion will be the thermal energy, and divided by the Boltzmann constant, you get temperature, and so on. Okay, all right. So, and the equations of motions are essentially conservation of mass, conservation of momentum, and conservation of energy. Conservation of mass, you get that no mass is created or no particles are created. So then at any volume, if you try to figure out what is the rate of change of that mass there, that will be governed by the flux that is coming in. Okay. So if you then use the divergence theorem and whatever, what you get is the continuity equation. Okay. Then you write down the Newton's laws for or the force law or the momentum balance, and then you do again this simplification. What you are left with is called either the Navier-Stokes equation if you have dissipation, or an Euler equation if you don't have dissipation. And then energy equation is essentially the first law of thermodynamics, okay, etc. And so this is the set of equations. There are 5 equations here. This in numerical simulations, these are not very useful form. The useful form is what we call the conserved form. That is, there is a time rate of change of a quantity, which is the divergence of its flux, should be equal to 0 or should have a source term, source or sink term. Okay, so that's the conserved form, and this is the equation we solve. Okay, I'm not going to talk about how these are being solved. What is the mathematics behind it? Forget it. Okay, for the time being. Okay. All right. So again, so these equations are not complete because the number of equations and the number of variables are more. I mean, the equations are less. So you have to use a closure relation. For if you use MHD, you need another closure relation. Okay. So 2 closure relations for MHD. For hydro, you need 1 closure relation. And the closure relation is a relation between the thermodynamic quantities. And if you use, if it is a Maxwell-Boltzmann distribution, you can show that it is a Maxwell-Boltzmann distribution. And you calculate the energy and the pressure and so on, they can be related. And it is something like, if it is a new, I mean, if the gas particles moving with Newtonian speeds, then you can show it, the energy is like this. This is, normal thermodynamics. But if they are moving with relativistic speeds, then it will be not so simple. It will have Bessel's functions, but those are difficult to handle. So we proposed another equation of state some 14 years ago, which is fairly popular now. So this is what we use. So, okay, so basically this is the internal energy. Theta is pressure by the rest mass energy density. Eta is the ratio of electron and proton mass, and xi is the composition, like how many protons you have per electron and so on.
Theta or equation statement?
No, theta is a sort of a measure of temperature.
Oh.
Okay. So if you do that, I mean, this is fairly good. There are many things, many checks here. I mean, how you know that this equation state is fine and correct? Oh, yeah. So I think it just shifted place. Anyway, so yeah. So that's what we solve here in the code we have written. Numerical simulation code we have written. That's the set of equation and equation of state we use. Okay. The BHL is a very simple thing. Okay, the simple thing is basically it's something like a trapeze, or maybe when your friends are playing around when we were kids. Okay, you see someone is running around and you try to catch that guy, right? But that's what you do. Okay, and so if you can catch him or her well, that fellow will come towards you, right? If you can't catch that fellow, it will leave. BHL is that. Okay? You have a gravitating center which is moving through a medium. Okay, we can revert that and we can say that this is static and the medium is moving, right? So the medium is moving towards the gravitating center, and whose impact parameters is such that the kinetic energy with which it is moving, if that matches with the gravitational potential at that point, then they will turn back. Okay, and there should be a critical impact parameter within which all the matter will be attracted towards it. And outside that, they might be tugged a little bit, but they will leave. Okay, so it's something like this. That's what I'm trying to. It's always a picture says 1,000 words instead of all the equations I showed, but this is what is going on. And that's again, if you it is beyond the impact parameter. In this case, you can catch the guy, it will fall, right? So that's what happens. So this is a schematic diagram. You will again see this diagram in that 1939 paper. Okay? And it is used in almost all fluid mechanics or accretion related textbooks. They use this figure. So basically, the critical impact parameter within which everything will be accreted or move towards the center, gravitating center, doesn't matter whether it's a black hole or any star. That radius, that distance is called accretion radius, or it is also called the Bondi radius. Okay, because Bondi, I mean, Hoyle and Littleton actually gave an estimate, but Bondi refined it for fluids. Okay, so that's why I wrote RB. B stands for Bondi. Hermann Bondi was Hoyle's too. Okay.
But the shock front, you are going to say that, I think.
Yeah. So why? But I have also written there is a shock here. So why shocks forms? First of all, you have to understand that what here gravity is doing, you have some motion independent of the gravity. What gravity is doing is stopping it and bringing it towards it, to the center, right? Okay. So this will happen whether it's the whatever speed that matter is moving. Okay. In interstellar medium, the temperatures are so low, it can be 10 Kelvin or something, right? So it's so low that a moderate speeds, okay, will make it supersonic. Okay. And if it is supersonic, then whenever you put sort of try to stop a supersonic flow or try to put some kind of resistance to a supersonic flow, what does it do? It shocks. Okay. All right. So what is a shock wave? Shock wave is essentially a sound wave. Okay. What does a sound wave do? Like I'm talking, my voice box is oscillating, right? So it is also oscillating the medium in front. And so this medium is pushing it, the next layer, and then coming back. So the next layer is also doing that. And then the next layer is also doing that. So it's a mechanical oscillation, right? And the energy that my voice box is creating is reaching you. And you hear it. And so essentially, this is a pressure and density perturbation I'm giving to this medium. And that pressure and density perturbation is reaching you. Okay? It's a wave. So the energy is reaching you. All right? So therefore, the job of a sound wave or acoustic wave, in general it's called acoustic wave, is to sort of disseminate a perturbation. If you have a perturbation, you try to sort of smooth it out throughout the medium. All right. Now this happens normally when the bulk motion or the what should I say, the mechanical motion of the source is less than the sound speed or the speed with which this is traveling. But what happens if it is moving faster? What it does is that, so if I am moving here, okay, and I'm also talking, so the speed with which it will move will be added, right, with my speed, right? And it will be a little less backward, but nonetheless, it will cover a larger region around me. But if I'm moving faster than this, then before the perturbation I'm creating can reach you, I'm reaching there, right? So the densities and the pressures cannot disseminate, so they will sort of pile up. Okay, until and unless within few what should I say, Debye length, okay, not Debye length, within few let's say the mean free path, the densities increases so much that there is, okay, all right. So there's some dissipation, okay? So you have bulk viscosity. Forget about what is viscosity, but it's again, I don't want to, so there is some dissipation. So what it will do is that it will try to oppose what is creating this, this very critical condition they are creating, where it's spiking up the densities and pressures, okay? That dissipation is sudden, and this dissipation is in a very small region, okay? And that's called a shock. So you dissipate the cause of this problem. That is, the whole job of acoustic wave is to distribute a disturbance. Here you're spiking it up. Okay, so nature has a way of stopping it, okay, through a shock wave, and therefore it generates entropy and so on. All right. So here same thing happens. So you form a bow shock, and then the matter is actually going in and enters. All right. So these are the models I use. Okay. So a lot of things I use. So I check if it is supersonic, just supersonic, if it's middle supersonic, which is highly supersonic, how things are moving. And I'm also changing the composition of the flow. Okay, I'm trying to figure out how they also behave. So you can see that in each model, you have some Mach number, and then xi is the proton proportion, right? So it is changing here. Again, then there's another Mach number, again it is changing. Another Mach number, higher Mach number, it's changing.
So all of them are independent variables? I mean, you
Which
can
one?
independently change the velocity and Mach number.
No. Mach number. So essentially, what I have done is I have kept the velocity same, fixed, and the Mach number I am changing. Therefore, the sound speed is changing. Okay.
But then temperature also is.
Yeah, it will change. So this RB is also changing, etc. Okay. So now some pretty pictures. Okay. So this is the simulation I did, and you can see that actually these are the streamlines. Okay. So you have the velocity vectors, add them up, the direction, and you get a streamline. And so this is the shock front. And you can see there is a null point here. This is essentially this size, and this size is exactly the same. This will give you the critical or the accretion radius, or the RB. All right. This is fine. Now, if I take one of them and change the composition, and you can see that the structures are changing, and this is for electron positron. And you can see that the shock front is much further. That is because for electron positrons have low moments, right? Momentum. And if you have low momentum, your sound speed should be also low. Okay.
So the composition, what is the xi? That is
xi is a proportion of protons.
Proton to electron ratio.
Electron, yes.
Okay, so that is okay.
Okay. And also the temperatures are also different. You can see for electron protons, it reaches around 10 to the power 10 to 10 to the power 11, while for electron positron, it is around 10 to the power 7, 10 to the power 8. Okay, so you can't even almost see it compared to the other ones. So now if I calculate how much matter is entering the black hole, okay? So if I calculate that in time, you can see this, it's changing. And it is also changing with respect to what is the composition I have. That is fine, that is not a problem. But all of it is around 0.8 of the Hoyle-Littleton accretion that Hoyle and Littleton 1939 calculated. And if you put believable numbers. For example, if you assume the accretor to be of mass 1 solar mass. You can say, how could you have a black hole of 1 solar mass, astrophysical black holes? I can't, but these are estimates. So if I take 1 solar mass and let's say it is that black hole is moving with 1% the speed of light through the medium, which is very high. Okay. Of density, say 1 hydrogen atom per cc, then the Hall-Littleton accretion rate is around 10 to the power minus 23 solar mass per year, which is very low. Okay, so for 1 solar mass to become 2 solar mass, it will take 10 to the power 23 years, which is okay. So it's not a very efficient accretion process. So if we calculate, I have not shown it here because the referee asked us to remove that because that's not real. I mean, when you show such low accretion, doesn't matter. Okay, you don't have to show the luminosity. So I'm not showing the luminosity here. But the point is the luminosity is very low to the extent it is below our detector limits. So whatever X-ray instruments we have, it is below its detector level. So it's no point in it. Okay, fine. So we know this problem. This problem, I mean, I have not talked about it, that when we were actually trying to explain through accretion the luminous AGNs and microquasars or the X-ray binaries. So the first model was matter falling radially in, which is called Bondi flow. Okay, relativistic Bondi flow. That was done, that was very fine, that's good, but its luminosity is very low. And people understood why it was low, because it is spending too little time. It is just falling in. Okay, it doesn't have any time to cook up all those photons that will be radiated. So what you need is matter to stay outside longer. Okay, so they went to this rotating flows. All right. So here the matter is actually, although it looks like it's forming like this and falling like this, it is not. You take a small area there around the black hole, it is actually falling radially. Okay, so it's not really spending a lot of time. So we need to make it spend some time. Okay, so the only way you can have it, if you have a stream accretion. What do I mean by stream accretion? Stream accretion is something like this. So you have the central object and you shoot it from the sides. Okay, a fraction of it will be captured, of course, but they will try to stay back. So when it is attracted, it will go there and then possibly it will overshoot. And when it overshoots, the gravity will try to bring it back. So it will rotate, right? Okay. So if I can do that, then it will be fine. Sorry?
So your initial equation that has that H star, isn't that angular momentum?
No. H star?
V infinity and H infinity.
Oh, that's H infinity? That is, where is H infinity?
That's M infinity. That's the Mach number.
Previous equation. Yes. When you are calculating.
Oh, this is RB. No, H infinity is enthalpy.
So that's not
Angular
moment.
But in that case, the shock wave is not created.
energy.
The shock wave will be created, but I'll show you how the shock wave is created. Okay. Time?
10 minutes.
10 minutes. I'll finish. It's okay. All right. So yeah. So then the previously the problem was I'm shooting from everywhere, right? So the ones that are going like this, the from the other side is also going like that, right? So they're canceling each other. So there was no rotation. Okay. Here there's a chance of rotation. Okay. So okay, I showed the table, right? So here you can see a spiral shock here, right? You can see this line.
Yeah, but that is continuously changing, no?
Yeah, that is changed.
Yeah, because all sides it is being shooted.
No, it's not. It is shot from one side, but I'll show a very nice thing later on. Okay, so that's
Indranil, at the center, I mean, that's the potential. Is that like infinite or I mean, what is the
we took
the same particle or something?
no, we just used Paczynski vector.
Okay.
So it will be if I take a rotating potential, then it will be it will impart some rotation as well. Okay, so this is fine, but not just that. So the most interesting part is, okay. So if you actually see the previous movie, just to show the central region, we got rid of the region from where we are, injecting it. Now, if you take both the part, so you see, we gave it an angle, but this is vacuum, almost vacuum, not vacuum, but almost vacuum. So the matter enters, but spreads, right? And when it is reaching the accretor, okay, the main, bulk of the matter is around here, but there's a lot of some matter also in this side as well, right? So what does it do? Okay, it's fine. Bulk of the matter is here, so part of it is going there, and then it will force a rotation that we saw in the movie. But what happens is, so this is the case we showed before. Okay, so it was rotating like this madly, and then suddenly it became a shock cone. Okay, what happens is when it is rotating, okay, some part of matter is also there, right, which is moving in the other direction.
You can stop the simulation.
Okay, so when these two match each other, okay, it will try to push it like this, right?
That's how the shock wave is.
Yeah, absolutely.
And you form a shock cone. All right, but that's not end of it. So there is a flip-flop instability, right? So it forms, but the matter from this side is trying to move like this, right? And the matter here is trying to push it the other way. So it will flip-flop. Okay. Do I have that simulation? I'll show you one simulation which was too heavy because we have to take a lot of cadence to sort of 200 frames to make that movie to see actually what's happening. That is I don't know, I will be able to show it in the PPT itself. Maybe separately I'll show. Okay. So now what happens is now it comes the competition between the inertia and the thermal energy. Okay. So the inertia will try to move it in this direction, and the thermal energy will try to spread it up, right? So the top one is for electron protons. Electron protons is the highest temperature, but electron proton also has the highest inertia, right? So in competition, when it comes, not always the highest temperature wins. Okay, the inertia also wins. So for the electron proton flow, it again reforms the disk. But when I'm decreasing the proton proportion, it is not coming back.
No, but the shape is changing, no, but that is
Yes.
because maybe because of the how it is getting the shock wave is created.
Yeah,
I'll show you.
the shock will be split much later. Once you decrease the proton content to so much, there the shock cone goes there, right? I mean,
No, here
No,
it's,
no,
it's
yes.
formed
Okay.
here.
I equal to 0.2.
0.2.
This one,
that
this
is
one
okay.
is forming much later because
That is
now, I mean, again, this is a competition, right? So when you are decreasing the protons too much, it is becoming so cold that the inertia is dominating. Okay,
So when you are decreasing the proton, that means there is more positive transfer.
more positrons. So this is the plot. I mean, okay, forget it. It's the details of what happens. Okay, so this is the angular momentum plot.
কিন্তু আগেরটা দ্রুত ব্ল্যাক হোলের মতো কি ছিল কেন?
ওটা জুম করছিলাম,
ও আচ্ছা।
আশপাশটা জুম করছি। So this is the angular momentum plot. This is the one for xi equals to 1 or electron proton, where the disk comes back. And this is with 0.5, the disk doesn't come back. Okay? So in the case of disk, in which the disk comes back, because of the inertia, it has moved to the other side. So it has a tendency like this. So it will come back. Okay? Here it doesn't. Okay? And this is the adiabatic index. This is the movie, the high cadence movie. It's not, it's too bad, too slow.
It's a little slow. Yeah.
Yes.
What you can do is you can, continue now and show the movie
So-
separately at the
So
end.
now you see, it's gone.
হ্যাঁ।
It will come back. So the black hole is somewhere here. It's too slow, but okay, I'll just
So it was a
Go ahead.
one-time injection.
no, it's continuous injection.
That's not showing here.
No, but I'm zooming it here, right?
So that's only zoomed.
So actually, a realistic one would be I have to lower the temperature much to a lower level, right? But if you do that, then the boundary radius becomes huge. I mean, then it's difficult to simulate. So I'm running after people to get some, computational time.
But now you have to.
Yeah. Not for this job. It's for something else. So anyway, this is the accretion rate, which is we have. So this is the matter that is entering the black hole, and this is the matter at other radius. The accretion rate at other radius. Of course, these are higher.
But
And-
it's similar. Does it
Similar.
change to the?
No, but for example, this is like more than an order of magnitude less. This is like few into 10 to the
No,
third.
when you had the symmetric flow,
No, it's not symmetric.
with respect to symmetric flow, has it changed much?
It is changed. It has changed about not about an order of magnitude it has changed. So if I now plot the luminosities can sort of be just above the detection limit. Okay, so now if we put not a static black hole, but a rotating black hole, which will impart more angular momentum, there is a possibility of detection.
But it is also for a particular extra proton fraction.
Yes. But that can be managed
Ah.
for a different. So slower we flow. I mean the slower matter I inject, the VR, the slow VR, that will put more matter in.
Ah, right.
Okay, so the gravity will be able to attract more matter in. So, but then my boundary rate is so high, so large,
That is gonna-
so then I have a problem.
So this is so you are saying luminosity, that's what, the Bremsstrahlung, what is the?
This is Bremsstrahlung and synchrotron, nothing else.
You would have to model the Bremsstrahlung synchrotron.
It is there. We have modeled that, but what I'm trying to say is only Bremsstrahlung and synchrotron.
No, I'm saying how to compute this luminosity, just by taking the fluid
Indoor
parameters
compare
and
with-
computing the Bremsstrahlung.
Rho, you have the rho, you have the T, and
That's right, so then the Bremsstrahlung emissivity or something.
right. But here we have taken, okay, I'm not showing that. It's not just the dipolar Bremsstrahlung because there are a lot of positrons and electrons. So with the quadrupolar, I'm also taking the quadrupolar. Okay, so yeah, so I'll finish it off here. So stream accretion can form disk. Subsonic injection forms bigger disk. I have not shown the supersonic injection. They form disks, but smaller disks. Spiral shocks may form, but disk may be disrupted and shock cone may form. And electron proton flow disk reappears. But for this xi, it doesn't. But for lower xi, for example, if I take an electron positron, it is not a physically viable scenario. But if I, for argument's sake, put it, then it appears that it never forms the shock. continues to rotate. Need to include the magnetic field and dissipating forces. Thank you.
It's not.
The density has become low because it has gone like this.
So
Compared
that it has
everything,
entered in this region that has.
everything is contrasted with this, right?
Oh, so
So it would have been better if I have only plotted with the what is it called? Just a minute. Trackers. If I put the trackers there, then that would show that all the matter that has been injected.
লাস্টে কি মানে আবার আশিকো ফিটারটা করে লাস্টে
আশিকো ফিরে আবার আশিকো ফিরে z equals to 1. But we have to check with proper dissipation and magnetic field. Of course, you have to make it 3D. This is 2D. We have to make it 3D to see that a part of the matter, whether it's coming out or not.
Okay, questions? Okay, ma'am.
Okay, so yeah, I was just maybe a very, very basic comment. So first of all, when we are so you have a black hole at the center. Now that is the source of your gravitational potential. So how to create, I mean, so that would depend on what is the mass of the black hole and all that. Right?
Now this is unit is m equals to 1.
So so suppose then if I have to think about real numbers or meaningful numbers, then can you give an estimate like what kind of situation are these things mimicking? When m equal to 1 means in some unit it is equal to 1, right?
Yes.
So what is the mass of the black hole?
This is standard GR, right? You calculate everything with m equals to 1.
No, I'm saying that
Then-
if I have to, so suppose when you are talking about comparing things with observations, then wouldn't it matter like shouldn't have to.
Oh,
compare
okay,
the
sorry. So
numbers?
that I think
But
uh,
it's not the luminosity, right?
yes,
So
for the 10,
did some scaling there.
10.
10 so.
M equals to 10 solar.
So the black hole is about 10 solar. Now, so is it possible to see like how this scenario, because there will be an effect of gravity also, and what's the gravitational potential being provided by the black hole that will also have effect on the fluid here.
Right.
So is it possible to see that maybe there is some threshold mass below which you don't see or things?
No.
like that?
Black hole is the most democratic one. Right?
Okay.
So it will show its, I mean, whether it's 10 to the power 15 solar mass black hole, or it's 10 to the power.
Accretion is universal.
No. I'm saying that the features that it will show
Yeah, that
will
will
be
be
exactly the
universal.
same. Only length scale and time scale
That's
will
what
change.
that's what I'm saying, that might have some limit on the observational capabilities.
So you see, it's very difficult to imagine supermassive black holes as runaway black holes or isolated black holes. Okay, it has to be 10 solar mass, few tens of solar mass, few solar mass. So we have just gave a ballpark number of 10 solar mass. Okay, and then you sort of scale up and down.
I think, an extension of that question is you showed that at the very end, you showed, okay, this is just barely above the detection limit, something like 10 to the 21 arcs per second, something.
No, 28, 29.
29. So how does that depend, that number? How will that depend on, so this medium that you're talking about, that is the interstellar medium, right? So the density of the interstellar medium, that will matter,
Yes.
or the mass of the black hole, or you showed that the content, the constituent will matter. So for example, the density that you consider to calculate that number, Is that what? That is the standard sort of.
So I
ISM
just
test.
gave you number for if I have one proton per cc, right?
Okay.
It's typical typical
ISM.
typical ISM.
ISM test.
But let's say we have, I mean, I can apply this for tidal disruptive events,
Right.
TDE. I have a star which I'm sort of
Right.
smashing it up,
Then you will have more density.
so I'll have more density. So then it will jack up. Okay. Or there is a stellar wind. I'm going through a stellar wind. Okay, the density will go up. Velocities will go up. Then 0.01 c may not be too high a velocity.
By the way, supermassive black holes could be run away in galaxy mergers,
Yeah,
but that's a different.
Might be, yeah.
It
But
could still be because even in numerical simulations, we do see this isolated supermassive black holes, like no accretion, nothing, just, but that could.
But anyway,
still be
that's a
still-
separate sort of.
I think there was a paper which Peter Van der Kolk and Postov.
There are some runaway-
Black hole runaway.
Suspected
Suspect
runaway.
of a- If there aren't other questions, I have a second one, but you can go to others.
Jyoti, do you have a question?
Okay. Sorry. What I was asking is, in the last animation we did, does that shock wave come again periodically, or is it a one-time event when we are?
no, it will come back.